Hi, and welcome to this presentation on monitoring and tuning Aurora Postgres. I'm Jeremiah Wilton, and I'm going to dive into this topic with you and hopefully provide some insight into how you can keep your Aurora Postgres clusters running efficiently. My job at AWS is to help build the tuning and monitoring tool set for our database services. Database performance tuning and monitoring is, as a lot of you know, a kind of black art. And every practitioner has a different set of tools and techniques that they use. Um, and in the world of tuning databases, expertise is at a premium. What we really hope to do at AWS is provide an environment where our customers don't have to be experts. What we want to do is make it easy to find bottlenecks and regressions, but more importantly, find solutions to your performance problems. And I've actually been at this for a while, actually since 1997, when I was lucky enough to be hired as Amazon's first database administrator. I actually think this photo is from 1998. And that's actually an important detail to add because our experience over all these years, for the past 24 years managing databases, has informed our designs for performance monitoring and tuning tools today in AWS and Aurora. Well, if you signed up for this webinar, you probably already know something about RDS and Aurora, but what you may not know is just how we ended up building these services and how we think about performance. So back in the 90s, we ran Amazon on relational databases that we managed ourselves using mostly manual processes. There were a few batch jobs and a few scripts that we wrote in shell script, but it was not something you could have considered full automation at all. And this was hard work, and it was a lot of labor, and it was especially difficult because we were scaling at that time at rates that were not typical of other companies that were using relational databases back then. So the combination of tuning challenges due to scaling and operational challenges due to our manual processes pushed us to develop new ways to manage our databases so that less engineer effort and time was needed in order to manage this exponentially growing estate of servers and databases. And it was exactly this expertise and know-how that we developed that we were developed back then to run Amazon, that we realized at some point in the 2000s that customers might like to benefit from. They might like to benefit from our tools and that experience. So that was the inspiration for starting AWS in the 2000s, and then RDS in the 2010s. So, basically what happened was we realized that our unique position managing thousands of systems at scale for Amazon could be translated into a hugely beneficial set of services for customers. So that's how AWS and RDS started. A big part of what RDS and Aurora do for customers is that automation. We basically automate the heavy lifting of managing databases day in, day out. And there are dozens of things that we automate. Just to give you a few ideas, with the click of a button, we provision. So you can provision a new database, including the host, operating system, and database. It all gets provisioned for you in minutes. We automate the scaling of that system, so you can scale that system up and down elastically according to your needs. And we even do it for you automatically and transparently in the case of Aurora Serverless. We also set up high availability and disaster recovery for you, so you don't have to do that yourself. We take care of regular backups, and in the case that if you need to recover your database, we automate that process too, including point-in-time recovery, which is actually a pretty complex process. There's way more than those examples, but sort of last but not least, I'll mention security as another thing that we automate. We actually let you, with the click of a button, specify encryption at rest for your database, right from the start when you create your database initially. Um, we let you set up auditing and other high-end security features that let you implement industry standard compliance. Um, so basically everything that you can do manually on conventional databases, we attempt to automate that in RDS and Aurora to take the labor over for you. Now, a lot of customers ask me, like, what is the difference between Aurora compared to RDS MySQL and Aurora and RDS Postgres? The community editions of those databases. Aurora is different because it's a cloud native database engine. We built it from the ground up to meet the needs of enterprise customers, higher end customers who are accustomed to those legacy commercial on-premises databases. Those legacy commercial databases are actually pretty good databases. They're powerful and full-featured, but they're very expensive and they do not translate all that well into cloud-native architectures. So we built Aurora as our answer to that need for our customers. Right from the initial SQL prompt, Aurora looks and feels just like a Postgres or MySQL database. But behind the scenes, it's a distributed, fault-tolerant, self-healing system that can auto-scale up to 64 terabytes per database. Each Aurora cluster automatically sets up replication for you. And that replication is across 3 availability zones for total resiliency. Aurora delivers high performance and availability with the ability to add up to 15 low latency read replicas. So in essence, Aurora is a cloud native and therefore massively scalable and available database. And Aurora is meant to address these high-end enterprise use cases in a way that MySQL and Postgres community editions don't do all by themselves. And we aim to do it at a lower cost to customers than those expensive legacy commercial on-premises databases. It's funny, it seems like my talks often turn into impromptu history lessons. I don't know why that is, but I think it will help explain how we ended up with the kind of monitoring data that we have now in Aurora Postgres. Back in the 90s, database tuning was pretty crude. We more or less looked to see what kind of resources a database was using. We looked at CPU, we looked at I/O, and then we tried to drive utilization of those resources like CPU and I/O down. One way we did that was by aggressively managing the proportion of I/O requests fulfilled by the database buffer cache, buffer cache hit ratio tuning. The problem with that approach is that it often made us target the wrong things. For instance, a SQL statement doing 100,000 I/Os that are all buffer misses might actually complete very quickly because of various kinds of optimizations, such as in the storage subsystem, storage disk read ahead, controller caching. So we could spend all day long tuning that SQL and win back very little latency on the query itself. Over time, it started to dawn on us, and it also dawned on the rest of the database world, that what mattered far more than resource utilization was database time. People don't care how many IOs or how many CPU clicks are consumed by a particular query. They only care about how long that query takes. If the SQL is fast, it's a good SQL. If it's slow, it's bad. So that's how wait events got invented. Wait events are a way to track how time is spent in the database. We use them to focus our tuning on things that will improve latency rather than on driving down resource counters. Oracle actually introduced wait event instrumentation back in Oracle 7 around 1995 or 1996. But people didn't really understand why it was important until the early 2000s. That's when people like Carey Millsap started writing papers on wait event profiling. That helped Oracle folks, Oracle practitioners, understand why wait events were important and start tuning using database time. But other database products like SQL Server lag behind in instrumentation and didn't really have wait events. Microsoft finally did add wait events, and then it took a while for practitioners to become aware of their value. We saw wait events turn up finally in MySQL's optional performance schema feature, then as a pretty fully developed feature in PostgreSQL version 10. So at this point, all the major database products have wait events, and they also have the ability to profile performance in terms of database time. But unfortunately, with practitioners of non-Oracle engines, this method, the database time and wait event method of tuning workloads, just hasn't caught on quite as strongly for whatever reason. In order to understand how we use database time to help customers monitor their databases, I need to introduce a concept and a metric called database load. Database load is measured in units of active sessions. Now let me explain what an active session is. It's a database connection that has made a request from the database, but that has not yet received a response. In other words, active sessions are connections that are busy in the database, not idle. They're connections the database is doing some kind of work for at any given moment. So if you look at this illustration, you can see that there are 12 connections, each behaving a little differently. Some of them are running longer queries that last several seconds, while others are doing almost nothing or are running very short queries in rapid succession. This is what a lot of real-world database workloads look like, very diverse workloads. So to get a clearer idea of what's going on in the database, we measure database load by writing a monitoring program to come into the database and measure the active session count every second. You can see here for each sample, we count how many connections are active at the moment of the sample. You can see the count down here at the bottom. So, for the first sample, we encountered 3 active sessions, 1, 2, 3. For the second, we encountered 3. Move further along, you can see over here, we encountered 8 active sessions, 1, 2, 3, 4, 5, 6, 7, 8. So, you can see that gives us a number that's actually quite easy to turn into a graph. And that graph represents the level of workload that's happening in the database over time. This is also called lightweight profiling by some people. I've measured active sessions here, but what about wait events? Wait events also need to come into the picture here to help fill out the understanding of what's happening. Wait events can actually tell us what these sessions are spending their time on. Here's the exact same graph, but with the wait event states of the sessions represented by different colors. You can see how the sessions are in various wait states at different times. But in the DB load graph, what we do is we just break the graph down by wait state. This helps us understand what the database is doing when it's busy. In this graph, we can see that the database is spending most of its time in I/O waits, this blue section here, and then later encounters lock waits, this green section here. So that is database load and wait events in a nutshell. Now, I'd like to show you how we can put this database load and wait event theory into practice. When you create or modify an RDS or Aurora instance, you can choose to enable a feature called Performance Insights, which does exactly what I just described. It samples the database every second and produces a live graph of workload. And it does several other things too, but that's the basic concept. And I'll go ahead and show this to you. When I log into the AWS console, I can, of course, choose from any of the AWS services that I use. What I'm going to do here is click down into the RDS console. And in the RDS console, I'm going to click on database instances. And that lets me see a list of my databases. Here we can see all my databases, and I want to point out the first place you can go to see how your databases are performing. Here in this list, we provide by default CPU, and database load indicators. If I just scroll it over, you can see that. The database load appears under the current activity column. And if you have performance insights enabled on your database, that shows up here as sessions. If you don't have performance insights enabled, we just show you the number of connections. Here you can see that there is an Aurora PostgreSQL database that's under heavy load. So like right here from the fleet view, you can see which database needs attention. It's very obvious in this view. All you have to do to drill in to see the performance is click on this current activity. And that takes us to Performance Insights. Here you can see that I'm running a TCC workload on this Aurora PostgreSQL cluster. And here you can see the database load graph showing active sessions broken down by wait event over time. You can choose a number of ways to look at the data, either bar graph or stacked area line graph. I personally like the stacked area line graph, so I'm just going to switch it to that. By default, this view will continuously refresh, but I'm actually going to pause it now to allow me to demonstrate a few features. So you can turn off auto refresh. Here it looks like the workload is split between wait events on CPU in green and waits on an Aurora Postgres an Aurora Postgres wait event called IO data file prefetch. And then finally, there's a third wait event that's visible called IO transaction sync. Now, looking at these, you might not necessarily know what IO data file prefetch or IO transaction sync means. And it's not a label that's descriptive or obvious to the average user. So we had to make a decision. We did want to preserve the native wait event names that come with PostgreSQL, but we also want to help customers understand what they're looking at. In this case, if I'm a user who's curious to understand the meaning of IO transaction sync, I can simply hover over that legend label and see an explanation of the wait, complete with suggestions for fixing it. Below the database load graph, Performance Insights lists the top SQL statements that comprise the load that is displayed in the graph. The SQL statements each have their own little bar graph showing their relative contribution to database load and their individual breakdown by wait event. So if we were curious which SQLs were primarily responsible for, say, the IO transaction sync waits, we can clearly identify them by this color, this sort of tan color in the graph in this top SQL list. You can drill into any one of these SQL statements to see the details of the SQL, including the full SQL text. You can also select a range from the graph by clicking and dragging. So here I'm going to click and drag across. So if there's a period you want to zoom in on, you can do that easily. Here I've zoomed in on a section that had some interesting artifacts that I wanted to look at. Most of the SQL that we see down here are prepared statements from the TPCC load generator that I'm using to inflict load on this database. And they're calling PostgreSQL functions. But if we look around, we can also see a few other statements like this. This one right here is a normal select statement, selecting the PG sleep function. I wanted to show you this because it illustrates how we're able to show you like all the different types of top SQL statements that are occurring on a database and their relative contribution to workload. So we aggregate these SQL statements in this view, and this lets you see the impact of those SQL statements on the database. Coming back to the trailing 1 hour view, so I'm going to go back to the top here and go back to the 1 hour. I want to show you how you can select one or more traditional metrics like transactions per second. Again, we use the PostgreSQL native name for the metric instead of substituting our own. In this case, the metric is transaction commit. To choose additional metrics, all you have to do is click on Manage Metrics. You can choose from a variety of database and operating system metrics in there. I'll go ahead and add a couple here. I'll add tuples fetched from the database metrics, and I'll go over to the operating system metrics, and I'll select total CPU utilization. Go ahead and click the update graph. And of course, when you look at these, now we've got all these new graphs in here. They actually align with the database load graph below. So whatever time frame you select in that in the database load graph will also be the time frame of the counter metrics, the traditional metrics above. Performance Insights lets you change the breakdown of database load in the graph. By default, we show wait events, but you can actually slice by any one of a number of attributes. Let's say I wanted to see the database load breakdown contribution by client host instead of wait event. When I choose slice by host, so you can see that the majority of workload is coming from my EC2 instance with that IP address. But some workload, mostly the Aurora Postgres background processes, are also visible there. Down in the list below, you can see that slicing by host is also reflected in the individual SQL bar graphs. So in this way, you can easily see which hosts a particular SQL is coming from. You can see that these top SQLs are coming from my IP address, and these ones down here in yellow are coming from the local host. As you know, this list shows you the top SQL by default, but similar to the load graph, you can list any of the other attributes in Performance Insights as well. So let's say I wanted to list the top weights instead of the top SQL. Well, I could go ahead and do that just by clicking on top weights on that tab right there. So that's a nice overview, I think, of Performance Insights for you. So another thing that you might that I want to demonstrate to you is enhanced monitoring. When you create or modify an Aurora instance, you can choose to enable another nice feature called enhanced monitoring. Enhanced monitoring collects operating system metrics and sends them down to your CloudWatch logs. So we're going to switch back to databases. We're going to go here. From the CloudWatch logs, you can actually bring those metrics into your own performance dashboards, or you can look at them in the RDS console. There is actually one other part of enhanced monitoring that I want to show you. To get to the enhanced monitoring views, you click into a DB instance page. So I'm going to click on my Aurora Postgres instance, and then you click the monitoring tab, which is right here. Inside the monitoring tab, there's a menu here called monitoring. So you click on the monitoring menu, and in here, if you choose the OS process list, you get a list that shows you the Linux processes running on your database instance. By clicking on the gear, you can actually choose up to 20 processes to view at a time. And in that process list view, you can sort by any of the columns that are displayed. We provide in here the most popular columns that you might be familiar with if you're a user of the Linux utility called top. Here, what I'm going to do is sort by CPU. And you can see like what the top CPU utilizers on this database are. And you can see that the top CPU utilization is coming from the Postgres database itself. And within the Postgres database, you can see which processes are consuming the most the most CPU. So you can see all these Aurora PostgreSQL backends. Now, most AWS customers run more things than just databases. So we made sure that RDS and Aurora can integrate seamlessly into AWS's overall monitoring service called CloudWatch. CloudWatch lets you create dashboards and set up alarms on metrics for all of your services. There's a lot to learn about CloudWatch, but right now I want to show you how you can add the database load graph from your Aurora PostgreSQL cluster's performance insights into a CloudWatch dashboard. So in the AWS Console, under Services, select CloudWatch. On the left-hand navigation, you can go down and select Metrics. Here you can see all the services that I'm running on AWS. There's DynamoDB, there's RDS, EBS, S3, EC2, all those things that I personally am running on there. Next, click RDS, and then click on Per Database Metrics. Here you can see a nice selection of metrics that you can choose from. There's lots and lots of them here. But let's say I wanted to add database load to one of my CloudWatch dashboards. So in this list, we're going to search for DB load. And that shows me 3 DB load metrics for each of my RDS and Aurora instances that have performance insights enabled on them. The metrics that it displays are database load CPU, and database load non-CPU. I'll select database load CPU and database load non-CPU for my instance. There's database load CPU, there's database load non-CPU, and it automatically updates the graph. Up above, we get this line graph, and it doesn't really look that interesting right now, but if we change the type to from line graph to stacked area, we actually get a graph that looks a lot like the graph that we saw in Performance Insights. Now, if we want to, we can add this graph to one of our CloudWatch dashboards. To do that, I just click on Actions and click Add to Dashboard. I'll create a new dashboard called PG dash. And I'll go ahead and add it to the dashboard. And that takes us to our new dashboard in CloudWatch. If I wanted to add graphs here from all my most important systems across AWS, I could. And that would let me create a dashboard, allowing me to monitor everything important to me in just one place. Besides all these monitoring tools, I want to highlight one more feature of Aurora PostgreSQL that directly addresses performance, and that's tailored to mission-critical workloads. And that's a feature called Query Plan Management. For years before I started at AWS, I worked on Oracle databases. And if you've ever worked on Oracle, you know there's a healthy concern that at any moment, for reasons that may not be obvious to anyone, the execution plan for a mission-critical query could change from one that performs well to one that performs poorly. If the query in question is part of, let's say, a retail website that handles millions of transactions per hour, then a plan regression, like I was just describing, could be very inconvenient for both the operators of that website and for their customers. Now, although Oracle is famous for it, other databases are not immune to sudden plan regressions. And Oracle customers migrating to other engines like Aurora PostgreSQL want to be assured that they can protect themselves against plan regressions. So for those customers, and really for any Aurora PostgreSQL customer that needs to be assured of stability, we introduced a feature called Query Plan Management. You can enable QPM with a simple change to your cluster and instance parameter groups. Once you enable it, the first thing you need to decide is whether there are just a few plans you're worried about keeping stable, or whether you want QPM to manage all the plans in your Aurora database. QPM only manages plans for statements that you want it to manage. You can manually add statements one at a time to be managed, or you can turn on automatic plan capture, and query plan management will manage all the SQL statements for your application. Once a statement is in QPM, it won't regress due to plan change. And QPM does not just lock plans in place, because of course your data may change, and it may end up being that new plans would be better. So with query plan management, you can also improve or evolve plans over time. So that's an overview of some of the performance management offerings we have for Aurora PostgreSQL. And let me give you a few pointers to where you can go to learn more about some of the things I've mentioned today. Here are a few places you can go just to get started. Some of these are landing pages, and some of these are documentation chapters, but you can learn more here about RDS, Aurora, Performance Insights, and Enhanced Monitoring. And for overall AWS monitoring, you can learn more about CloudWatch. And for those who want to manage the stability of their execution plans on Aurora PostgreSQL, there's query plan management. Thanks again. And at this point, I can take any questions from the Q&A chat.